Okay. Which is okay. So it seems it's time. So I will start. So hello everybody. This is Luboš Pirkl from CFD Support, and in today's webinar I will present the Turbomachinery CFD, which is CFD simulation software for all standard rotating machinery. The test case for today will be a water pump. Yeah, just for your information, in case of any technical problems, feel free to contact me later on in the future, and I will gladly answer all your questions and reminders. Okay, maybe I should. I will. Yeah, this is me. Hi, and I will share my desktop. I guess that would be a better way to show something nice. Okay, so today's webinar is going to take about 1 hour. In the first half of this webinar, I will show you how to simulate a water pump. In the second half, there will be a Q&A session dedicated to your questions and my answers. Okay, so I will start with a brief description of Turbomachinery CFD. So basically, Turbomachinery CFD is a unique software based on OpenFOAM. It was designed for allowing CFD simulations of all rotating machinery, such as pumps, fans, compressors, turbines, and water turbines, both radial and axial machines, both compressible and incompressible flows. And yeah, it's pretty comprehensive. It's really modern software. Maybe I should just put just a quick review of its unique value proposal. So Turbomachinery CFD is unique for the number one is Turbomachinery CFD has no licensing policy, which means our clients can keep Turbomachinery CFD forever, and they can use it for unlimited number of users, jobs, or cores, and that gives their investment into Turbomachinery CFD a permanent value. So number two is Turbomachinery CFD is fully automated, which means all the workflow can be run by a single command or by a single click. The case setup and machine geometry is being read from a single file, and all the process is being done automatically. So the OpenFOAM case is written down, the mesh is created, the case is set up, simulation is done, and finally the full results report is written down in HTML format, and that's ready for your web browser. So yeah, number three is the Turbomachinery CFD is open source. That makes it easily customizable for your own purposes, for your own workflow, for your really custom work. And the last one would be the real tutorials are included, so the user has no doubts about the best practice settings. and can use these settings from similar tutorials for his own simulations, for his own work. So it's really the best practice is available. There are also many other benefits of using Turbomachinery CFD. I'm not going to go for all of them. Feel free to contact me. I will gladly describe everything in details. Just for now, I will start with the pump case. So perhaps the most important information from today's webinar is all the information is available online. So you can go to our website, which is cfdsupport.com, and there in products you can find the Turbomachinery CFD very at the top, and there you can, if you click around, I'm sure you will find all the important information. So the information is available online. There are all manuals or step-by-step instructions how to run the software, how to put the data in, and how to pull the information off. So okay, so Turbomachinery CFD is available both for Linux and for Windows. So the workflow is the same. So you can, it's your decision, it's the user's decision. You can use Turbomachinery CFD in Windows and as well as in Linux. Turbomachinery CFD is transparent, so the trial version is available it's for free for everybody. It's free for 1 month period, so anybody can try Turbomachinery CFD, and afterwards he or she can decide to buy or not. So it's really transparent and really you have all the information to make the decision to buy or not. I will start with the case. So in today's webinar, I will work from Windows system. So I'm in Windows 10. I have installed OpenFOAM for Windows and then Turbomachinery for CFD demo. The Linux workflow is exactly the same. So everything I do here today, you can do as well in Linux, and everything would be the same. Turbomachinery CFD workflow is fully served from a graphical interface. So there is a graphical interface provided by ParaView. Of course, you can also work from the terminal. Some people prefer to work from terminal, so it's their choice. Again, it's the user's choice. So you can work from terminal or from the graphical interface. More people choose graphical interface, and also this webinar will be like in this graphical interface. And I will in case you would be interested in running from terminal, just let me know, and I will tell you all the information how to do that. And also some information is available online. Okay. So let's take a look at the pump tutorial. So by the way, all the tutorials can be downloaded from our website. Again, I will jump to our website, and in section download, very at the top, you can go to download cases, and there you can see many test cases or tutorials are available. So you can, for example, click at the pump, and there you perhaps you should put your email, and you can download the case pretty easily, and this is how you should start. Okay. The aim of this pump simulation is evaluating the pump head, pump flow rate, pump torque, and of course the pump efficiency. Those are the most important performance values. All the design engineers are interested in these performance numbers. So we will do the simulation in today's webinar. And okay, let's go for it. So there is okay, maybe I should say what's the input. So the Turbomachinery CFD is a system based on OpenFOAM, and the input is always like the CAD geometry, which is a surface geometry provided in STL format, which is a typical output of many design systems or of many AutoCAD or CAD systems, and the configuration file. So there are these two: configuration file and surface geometry. So configuration file is a simple file. I can show you how it looks like for the pump. It's really simple plain text file where some keywords are specified, and this is basically how the workflow works. So Turbomachinery CFD reads this configuration file, and together with the configuration file, it reads the surface geometry, and then do everything for you. Really do the whole simulation process. Creates the mesh, run the simulation, create the simulation report, and give you all the results. So there's the surface geometry, there's a configuration file, and yeah, and that's the input. So okay, when starting a new simulation, you can write your own configuration from the scratch, or the most effective way of doing any case is to modify an existing tutorial to your case you want to simulate to your purposes. So of course you can write everything from the scratch. If you when you open the configuration file in this paraview, all the settings is in your left hand side bar, so you can prescribe what's the just all of them: the coordinate system, all the physical settings, geometry parameters, what will be the results, what will be the format. It's pretty. There's everything you need for your simulation. Yeah, and that's how it works. Okay, so we have this pump. This is the surface geometry of the pump. By the way, this pump was designed in software which is called CF Turbo. I can show you a little bit. I have opened it somewhere here. Okay, so okay, so I'm in CF Turbo software right now, which is special design software for rotating machinery. It's developed by German company, CF Turbo, the same name as the software, CF Turbo, and it's a really great and smart design tool for designing all the rotating machinery. So perhaps okay, yeah, I can briefly just show you. You can set everything, you can change everything, you can design everything in the there's some meridian view. You can do so many settings here. You can watch your model all the time. And what is important, for example, in our company in CFD support, we use CF Turbo for designs of turbo machinery. The both softwares are like connected via interface, so you can export from CF Turbo to Turbomachinery CFD, and then you can directly go and just directly simulate really automatically, really smart process, really nice. Okay, so I'm back in Turbomachinery CFD. So the surface model comes from somewhere. Either it comes from some design tool like CF Turbo, for example, or it comes from your own design process, or from some CAD. Anyway, there is the surface model. There is the configuration file, and that's the input. Okay, so maybe I should show how Turbomachinery CFD works from the scratch. I will show from the scratch. So I will I have something which is running here. It's the calculation. Okay, I can comment just briefly. So you okay, I will abort this. I will say abort this calculation. So it's aborting. So it's going to be closed in a second, and I will start from the scratch. So I will show you how to start from the beginning. So for example, here I have one configuration file for the pump. It's called pump.tcfd. So all the Turbomachinery CFD configuration files has the extension tcfd. I'm in Windows, so I can directly click on this configuration file, and it shows me a paraview window. I click apply. Yes, and it gives me my Turbomachinery CFD input, which is the surface geometry, those STL files. It's created from three regions: the inlet tube, the impeller, and the volute, and also the configuration file where you can see those are like, I don't know, some inputs where is specified how many regions I have, what are the names of particular STL files, what is the inlet, what is the outlet. So it's pretty straightforward. And for example, the simulation constants and all these things are there. So here's the input, and what I do next is I apply the tcfd manager, which is a special filter in paraview which allows me to handle the simulation itself. So for doing the simulation, I need to apply the tcfd manager. It's Turbomachinery CFD manager, which is a typical filter. You can find it in filters. It's the colored arrows icon, which you can see in your menu. And yeah, and once I did this, I can go to do the simulation, to make the simulation run. So the very first things, or the very first thing I do all the time is I need to write the case. That's what I just clicked the button write case. So the case is being written down on the disk. The OpenFOAM case is has been written, and then I can, for example, click here to create mesh, and the mesh is created. Then I can click run the calculation, and the calculation is run. I can skip between points. I can skip between speed lines. I can abort the calculation. I can say abort and write the results. And what is important, I can anytime update the report with these results. And all these steps I can do by a single click. I will click run all, and this run all button, I'm doing it now, so just right now, and this run all button will do everything for me. So it creates the mesh, it runs the calculation, it computes all the points one by one, all the flow rates, all the pressure drops, which I have put into configuration file, and give me the results. So I can see the progress. So now it's meshing the second component. So okay, so the case is running. Okay. Okay, the case is running. Yeah, I can update the report anytime. And yeah, okay. Okay, maybe I should say a little bit to the input. Go back to thinking about what's the input. So again, the surface geometry is geometry which consists from a number of components. There's the inlet tube, which is basically waterproof. All the components has to be, all of them have to be waterproof, which means if you put water in, it should not just flash out. It's really all of the components should be waterproof. Each component should have the inlet and the outlet, and the walls and blades and hub and shout and all these things. So that's quite important. Maybe I should go a little bit back to introduce the configuration file, because now my CFD processor is still doing the mesh, so I can give it some time. Okay, so I'll go, perhaps I can go one by one in the configuration file. So Turbomachinery CFD configuration file has some general settings. You can specify the type of your machine. It can be compressor, fan, pump, turbine, or water turbine. It doesn't matter if it is axial or radial. You specify where your configuration file is physically located on your hard drive. You specify coordinate system. The origin is any point of the axis of rotation. Axis is the directional vector of the axis of rotation, which is z, x, y, z. So it's z. Geometry parameters, you can scale from millimeters to meters. You can use feature edges for SnapX mesh. Physical settings, you can use gravity or not, but by default we compute without gravity. You can go compressible or incompressible. So this is water pump, so we compute like incompressible flow. You specify the dynamic viscosity. You specify reference density. You specify reference pressure, reference temperature, also the fluid. You can choose to evaluate the cavitation risk function object. So we say yes, and then you can say there will be number of speed lines. So I will compute just one speed, one RPMs. Rotation speed can be set in radians per seconds or rounds per minute. Okay. This speed line will have 3 points. Each point will compute for 500 iterations. If not stopped by the convergence check, I can describe later. Inlet boundary condition would be the volumetric flow rate at the inlet. So we will compute 3 flow rates. The first one will be 186 liters per second. The second one would be 156 liters per second, and the third one would be 126 liters per second. There is turbulent intensity, turbulent dissipation. Those are inlet boundary conditions, outlet boundary conditions. There will be fixed pressure. I will simulate on 4 processors. There are some bounds for some limits for velocity and for pressure. I can use first or the second order numerical scheme. I will do my averages over last 100 iterations. Yeah, I will check the convergence. If the case is converged, I can stop. Bind to core is the processes will be locked to the physical cores in your computer. I say yes. There are some initial conditions. There are components. Okay, and here is the first component has like 3 STLs: inlet, wall, and outlet. And the second, the impeller has some hub patches, shroud patches, blade patches, inlet, outlet, and the volute has again some inlets, outlets, and RSI connection. Yeah. Okay, mesh settings. Yeah, this is pretty important. Background mesh size. So I say here 12 millimeters would be the basic background cube, which is very important parameter, because with this parameter you can handle the mesh size, and the mesh size is very important for every CFD engineer, because the mesh size gives you the order of the time the case will converge. So smaller meshes converge faster, of course, and the bigger meshes converge some more time. Yeah, the internal point has to be specified for snappy hex mesh. The cylindrical mesh can be used, but it's pretty advanced settings. Okay. So I'll go back to my CFD manager, and I can see, yeah, it's computing already. So the first point is being computed. Yeah, I'm in my like 10th iteration from 500. So 28 minutes are remaining for this point, and 1.5 hours is remaining for all the simulation. Yeah, I'm sitting at pretty slow computer. It's laptop. It's has pretty low performance, so it's gonna take some time. Perhaps after some time I will skip to the next point, and I will stay satisfied with the current numbers I have up to in the meantime. So I can report. I can update the report anytime. So I'm updating report. You can anytime during the simulation you can click update report, and it gives you the new report with current results. So here it is. So I'm maximizing the report window, and it tells me, yeah, somewhere in the very beginning, but I can see what are my some statistics. So what are the mesh size? What's the mesh size? Yeah, I'm running on 4 processors, and by the way, this laptop has 2 processors, so it's maybe a little bit too much. Yeah, so you can see how the flow rates are doing, how they converge the inlet and the outlet of the whole machine. You can see the residuals. Yeah, you can see the efficiency. Maybe I should update once again because these results are too early. So I'm updating my report again. Okay. Okay, so it's converging. I can see the residuals are going down, flow rates are going closer and closer one another. Efficiency is going to go somewhere to 80%. Yeah, my torque is going to converge. Okay, so it's going to take some time. Yeah, so I can stay all the time here in ParaView. So everything is done here in ParaView. I can set my case here. Then I can write it down. Then I can just run all the automatic workflow. So Turbomachinery CFD is extremely effective because you can do so many simulations in parallel, just quickly. You don't have to do many settings because many things are already preset. So you can decide on your own how deep you go in detail, how much time you spend with going in details with your simulation. So it's extremely effective. Okay, so the first half hour is gone. So perhaps it's time to give some questions and answers. So I will stop sharing. Okay, so may I ask if there are some questions? Okay. Yeah. I yes. I can see there are 20 viewers here, and the way how to put the questions is, well, I will click here. Okay, I will take a look at the webinar. Okay, I have to say I can't see where the questions are, so it's really okay. Okay, so once again, I will. This is my. Okay, so well, once again, I will check Q&A. Okay, it seems to be okay, I can't. Okay, I can't find any questions. So let's. Okay, so the only things the only idea I have is um, and basically I can't find any question. So okay, so what can I do? So we should I'm gonna I think this should be it. So this is it for today. So uh, if you well, I would ask you if you have any questions on Turbomachinery CFD, just send me an email. I can show you uh, my contact information, which is again I can share you my screen, and the best way how to stay in touch and answer your questions would be if you yeah it's here. So I guess you can see this. So please be so kind, give me send me an email, and I will do my best to answer all your questions and reminders. Yeah, I always I always apologize if something were not very perfect in detail, because this is our first webinar. So feel free to contact us. We will do our best to answer all your questions. And I guess this is it. So I guess this is it. So okay, so let's stay in touch and feel free to contact us, and we will answer all your questions. We will really give you all the information, and then you would be able to make any decisions. Uh, okay, so thank you for your time, and yeah, just let's stay in touch. So bye bye.